it's fine.
Okay, we can try it again.
Okay, all right. Well, thank you everybody for coming, and thank you to the organizers, both for the very nice month-long program and for including me. I'm very happy to be here. And the theme today is applications of p-derivations to mixed characteristic commutative algebra. So we're sort of continuing the theme of Jack's talk on Friday, but today I want to tell you about applications to symbolic powers. And this is a joint project with Alessandro Stefani and Jeffries. And I will tell you a story with two parts. I will first tell you about a result from a few years ago that maybe some of you have heard of before. And then in the second half of the talk, I'll tell you about a recent follow-up that we just put up on the archive a month or two ago. So I want to tell you about applications to symbolic powers specifically. And even though I know there's some experts in the audience, I think there's also some non-experts. So I thought I would start with a brief introduction to what are symbolic powers and why would you care about them, or some of the reasons you would care. So I want to talk about radical ideals in Noetherian rings. If I ever forget this assumption, it's always in the background. And the n symbolic power of I, which I write sort of like a power, but with a parentheses up here, is computed the following way. You look at the ordinary power, so the ideal generated by the n-fold products of things in I, and you're going to localize it at all of the associated primes of I. So notice these are the minimal primes of I, in fact, by my assumption. So the minimal primes of I to the n, and then I contract back to R. So what I'm really doing is I took the ordinary power, I computed a primary decomposition for it, and then I collected the minimal components and threw away the embedded ones. So symbolic powers are difficult to study, in particular because they come from primary decomposition, which is difficult to study, difficult to compute. And in fact, a theorem I learned from Mel Hochster a few years ago at a conference says that we don't really know anything about symbolic powers, or almost anything. And really, most natural, innocent sounding questions you could ask about symbolic powers are essentially open. But there are many reasons why we'd want to know more about symbolic powers. And to tell you of a couple of reasons, one of them I'm going to make it very precise in a minute. I'm going to tell you that if you're over a polynomial ring over a field, these are the polynomials that vanish to order n on the variety that I defines. But besides this sort of geometric information that they contain, they also appear as auxiliary tools in the proofs of various classical results. So just to give you a couple of examples, they appear in the proof of Krul's-Height theorem and in the proof of Hartshorne-Lichtenbaum vanishing theorem for local cosmology. So two results that have nothing to do with symbolic powers, but whose proofs involve these as tools. So these are some of the reasons why maybe you'd want to know more about them. So let me tell you some things we do know. And I'm going to write some elementary facts that I will need later in the talk. So they're good reasons why I want to write these for now. So first of all, if I'm talking about a prime, the n symbolic power is just the elements that live in the power up to multiplying by something not in P, right? So to make this very explicit, this is the smallest P primary ideal that contains the ordinary power, right? So it's the P primary component of P to the n. So in particular, there are ideals that always contain the ordinary power, but I want to emphasize that in general, they are not the same. Like, this is not the theory of powers. Otherwise, it wouldn't be so interesting. But they do satisfy some properties that you'll recognize as properties that powers also have. So for example, they're a descending chain of ideals. So I take a higher symbolic power, I get a smaller ideal. They form a graded family of ideals. So in particular, this allows me to construct a graded object out of taking symbolic powers. So an object that in degree n has the n symbolic powers, sort of packaging together all the symbolic powers. This is known as a symbolic Riesz algebra. And it's something that even in simple situations for primes and polynomial rings over fields can still be infinitely generated. So you might find elements in arbitrarily high symbolic powers that are sort of unexpected in some way. And there are situations where these indeed are the powers. So here's an easy one. If my ideal is maximal, then indeed the symbolic powers are the ordinary powers for silly reasons. Here's a proof. An embedded prime of m to the n would be a prime that strictly contains m, and obviously no such thing exists. So the ordinary powers are indeed m primary ideals. Now, another situation where we have equality is if I have a Cohen-Macaulay ring and I have a complete intersection ideal, so an ideal generated by a regular sequence, then again, the symbolic powers are the powers. But these are only sufficient conditions. They're not necessary. So there are other classes of ideals where we have equality. And in fact, even the question of for which classes of ideals do we have equality between the powers and the ordinary powers is not as well understood as we wish it was. So let me show you some very simple examples. Maybe some of the first examples one ever sees. So here's many people's favorite monomial ideal. So this is a situation, a rare situation where I do know a primary decomposition by hand, right? I can just write it out. So it's the intersection, the union of the three coordinate lines. And if I want to take the symbolic powers of this ideal, I would look at each of these three minimal primes, take their symbolic powers and intersect them. But these primes are generated by variables, so their symbolic powers are the powers, maybe by my number 5. And so this is just the intersection of the powers. However, I want to emphasize that the intersection and the power don't commute, right? And so in particular, here's an interesting element in the symbolic power. XYZ is in the second symbolic power, but it couldn't possibly be in the power because it has, for example, degree 3, and the square, of course, is generating degree 4. So this is a very common situation where you find elements in your symbolic power that are sort of on the wrong degree, okay? And we'll see this will come back later. So here's another example, maybe an exercise for the board audience member. If I have a 3x3 generic matrix, so fill it with 9 different variables, take any field you like, take the ideal of the 2x2 minors. So this is a prime ideal in the polynomial ring generated by the variables that I put in my matrix. So prime, for emphasis, prime in a polynomial ring. And you can show, for example, using, you can do it by hand, you can use a theorem I'm going to tell you in a few minutes, that the determinant is in the second symbolic power. But again, the determinant is an element, curiously, again, of degree 3. And again, my ideal is generated in degree 2. So this couldn't possibly be in the square, which is generated in degree 4. Okay, so same phenomenon again. Now, the story I want to tell you today really starts in the late 40s with a theorem by Zariski in 1949. And then it continues with Nagata, which sort of completed that theorem in his local rings book. And then there's a more modern treatment of this, a generalization by Eisenbud and Hochster in 1979. And the theorem says the following. Let's say that I now take a prime in some finitely, I'm sorry, there's a funny bug in my my pencil, and I've been too busy to go to the Apple store and get it fixed, which is a little embarrassing. But anyway, so let's say I have a finitely generated K algebra. So here K is a field. Truthfully, what I need is a Jacobson ring. And the theorem is, first of all, the n symbolic power of P is going to contain the intersection of the powers of the maximal ideals that contain P. And then when the ring is regular, so this first thing is really Zariski's result, and the second part is Nagata. So when R is regular, we have equality. So this is a theorem I said really fast in the beginning of the talk. This is telling us that if you have an element that vanishes to order n on every single point in the variety that the P defines, then it's precisely in this n symbolic power. Okay. Now, if you're in the local setting, this couldn't possibly be true, right? The symbolic powers are not the powers of the maximum ideal. However, and let me call this the Zariski-Nagata theorem. I apologize, I'm going to call various things the Zariski-Nagata theorem, but I'll try to make it clear what I'm referring to at each point. So if I have a regular local ring, there we go again. If I have a regular local ring, then what we can say is that the n symbolic power is contained in the nth power of the maximum ideal. And in the second half of the talk, I want to come back to this result. And you might forget it in the meanwhile, but I'll remind us of it when it comes back. Okay, so what I want to do is I want to rewrite this result. Okay, it's not completely a rewriting, but I want to give you a version of this result. And that's the thing I'll really call the Zariski-Nagata theorem, now using differential operators. And as an appetizer for the general result, let me first tell you the result over C, and then I'm going to write the general version. So I want to be now in a polynomial ring over C. So again, I take a radical ideal. So I guess I declared this in the beginning. I didn't have to write it. And the theorem is that the things in the n symbolic power are the polynomials that live in I after I apply, and now, sorry, it's going to take me a minute to write. I'm going to apply various partial derivatives to this polynomial. So dx, d, and d. And I want to still land inside of the ideal I, so still vanish on that variety, whenever the order of the partial derivative that I took is at most n minus 1. And maybe it's worth it for me to pause for a second and say, so it seems like this is a little off. The point is, if you take the first symbolic power, you want the things that vanish to order 1 on your variety, so the things that vanish there, right? So you want to do nothing, right? When this is 0, you did nothing, and f was an I. Okay. Okay. So I said this was an appetizer for the general results over other fields. And what I want to do in the general setting is I want to replace these partial derivatives by writing differential operators of certain orders. So I want to remind us all of Grothendieck's definition of differential operators. So I have an A algebra. And I want to talk about the A linear differential operators on R. So what they are, so the different A linear differential operators on R, and by the way, A here for now could be whatever ring you want, doesn't have to be a field for this definition to make sense. So this is going to be some collection of A linear maps on R. And I'm going to give you a filtration for it. So I'm going to tell you inductively what are the what are the differential operators of order up to n for each n. So for order 0, the differential operators of order 0 are just the R linear maps. So if you like, these are multiplication by elements in R. And then if you give me something that is an A linear operator on R, this is indeed a differential operator of order up to n if whenever you take its commutator with any element in R, so really with any order 0 differential operator, I want this commutator to now be a differential operator of order n minus 1. Okay, otherwise this wouldn't really mean anything. Okay, good. So now with this definition, if I was over C, the differential operators over C are the k-span of all the partial derivatives that I can take. So the ones of order up to n would be precisely the ones where the sum of these goes up to n, right? So what I wrote here, now I'm going to give you a general definition of this. This would be the nth, maybe I should write it down, nth differential power of I that I can define for any ideal in whatever circumstances. This is going to be the set of elements that are now sent inside of I by all differential operators of order up to n minus 1, right? So for emphasis, this is what we wrote upstairs over C. So the general Zariski-Nagata for differential operators is that now if I'm over a polynomial ring over a perfect field, and I take my favorite radical ideal, its symbolic powers are precisely its differential powers. And I do want to point out, so this fails if K is not perfect. It fails if you're over other rings. But I do want to note for later, and again, I'll remind you of this fact later, that even when K is not perfect, I still have this containment, actually in much bigger generality. I still have that the symbolic powers are contained in the differential powers, and that's going to play a role later in the talk. Okay, so the first question that I want to answer today is the following. I want to know if it would be possible to give such a theorem in mixed characteristic. And if I want to keep everything mostly the same, I'm in big trouble. So in mixed characteristic, this can fail in a dramatic fashion. So here's a simple example. Let's say that I take Z and I join one variable. And let me take the maximal ideal 2 comma X. Okay, very, very simple maximal ideal. You might remember I said earlier, the symbolic powers of a maximal ideal are just its powers. But however, I claim that for every n, the differential powers are strictly bigger than the ordinary powers. For every n, at least 2. And here's why. Okay, so first of all, what happens for the second differential power? The second differential power is governed by partial derivatives of order 1, right? So it's really governed by ddx. What does ddx do to 2? It sends it to 0. Okay? Even worse, if you take any differential operator in my R that's now zilinear, because it is zilinear, what does it do to 2? Well, it sends it to 2 times wherever it sends 1. But that, of course, isn't the ideal generated by 2, which is contained in the prime we were talking about. So this in particular is saying the 2 is in every single differential power of m for all m. So somehow differential operators, because they're zilinear, they cannot see what's happening for prime integers, right? Of course, you could say, well, the problem with your example is that this is an ideal that contains a prime integer, right? If it didn't contain a prime integer, maybe we wouldn't have this problem. And indeed, one can deduce that from the version for fields. So with Alessandro and Jack, we show the following. So let's say that you're over Z or over a DVR with uniformizer P, some prime integer. And let's say that your ring is the localization of some finally generated smooth A algebra. And take your favorite prime. That does not have the problem that our example did. So a prime that has nothing in A. Then indeed, the differential powers are the symbolic powers for all n. So the differential operators do see everything they have to see as long as there's no prime integers in the mix. However, this is sort of not the main point I want to make, right? I'm more excited to explain what happens when I do have a prime integer. Like, how do I fix what was going on with this simple maximal ideal? How do I describe its symbolic powers? And in a way, the problem, the difficulty that I have here is that I need something that's going to decrease the p-adic order of P in some way, or decrease the p-adic order of elements in general. Because I want to somehow see that, say, 2 should be sent by some operator outside of this maximal ideal, right? So it should go to something of, let's say, 2-adic order 0. And if you were here on Friday, Jack also told us about some mixed characteristic stuff. And he told us about p-derivations, which are, as he told us on Friday, and I'm going to remind us in a minute, they are operators that, in a sense, decrease p-adic order. They sort of behave like DDP, right? So they're sort of the right thing to add in here. So maybe let me move to the next page. Definition. So this is an independently defined by Buium and Joyal. And if you were here on Friday, Jack gave us a very nice introduction to p-derivations. So I'm going to say a little less, but just in case you've forgotten what you've heard on Friday over the weekend, or maybe you weren't here on Friday, I will remind us of some of the basic things about p-derivations that I'll need, but maybe leave some of the details since we just heard them on Friday. Okay, so let's say that you take your favorite prime integer, and let's take a ring. I don't need this assumption, but it's going to be in all my examples, so it's going to make the story easier. I want that P is not a 0 divisor, so it doesn't send anything non-zero to 0. A map from R to R is called a p-derivation if it satisfies 3 axioms. So for all elements in R, I want the following things to be true. I want 1 to be sent to 0. I want a rule for sums. And I should say, I think most of us are used to thinking about additive maps. Right? So this is the rule you're expecting me to write, but this is not an additive map, unfortunately. Or fortunately, maybe that makes the story more exciting. So I have to add in a little term here that's going to compare the difference between the sum of the piece powers of my 2 elements and the piece power of the sum divided by P. And then I have a product rule that should sort of remind us of the Leibniz rule. So, but then I kind of twist things by taking some piece powers and by adding in a multiple of P at the end. And so anything satisfying these 3 rules is a p-derivation. And maybe repeating some things we've heard on Friday, one of the ways to think about p-derivations is the following. So note that if you have a p-derivation that is exactly the same, it's equivalent to having a lift of the Frobenius map on R mod P. On R mod P. So what does it mean to have a lift of Frobenius? So I want a ring homomorphism that sends each element to its p's power plus something, some sort of correction term to make it a ring homomorphism that lives inside of P. To have a ring homomorphism is to have a map that sends 1 to 1, preserves sums and preserves products. If you wrote down those three things and rewrote them in terms of this delta, you would discover exactly the three axioms that I wrote up here. So this was cooked up just right, so that a p-derivation corresponds to a lift of Frobenius. So given a lift of Frobenius, the corresponding p-derivation would compare our lift of Frobenius with the actual power and divide by p. Okay. And you know, we don't always have lifts of Frobenius, so we don't always have p-derivations. And on Friday, Jack gave us a nice list of examples. In fact, he gave us several examples where there aren't p-derivations, examples where there are. I'm going to only focus on a few examples, the ones that I'm going to need for today's results. So here's situations where I do have a p-derivation. Over Z, we have a p-derivation. So when I go mod P, the Frobenius map is the identity, right? That's the Fermat's little theorem. So when I lift up to Z, the identity map will be a lift of Frobenius. So the map that sends n to n minus n to the p over p, this is a p-derivation on Z. In fact, if you look at our axioms, we know 1 goes to 0, and we know what it does to sums. So what it does, you know, on any ring, what it does to its prime ring is uniquely determined. So in fact, there is a unique p-derivation on Z. And moreover, on any R, if you do have a p-derivation, any p-derivation, sorry, I'm going to write p-der, does satisfy this formula for elements of Z. Right, so for elements in the prime ring. Great. Another situation where I know I have p-derivations is if I have a complete unramified DVR with perfect residue field. And then more generally, suppose that you handed me a ring that does have some p-derivation on it. So for example, one of the ones I just listed, maybe let me call it delta, and I take a polynomial ring over that ring. So B, join a bunch of stuff. Then I can extend the p-derivation on B to my entire polynomial ring by sort of sending the variables to whatever I want. So let me just say, set the images of the variables freely, okay? So for example, you can send them all to 0. And this is one of the examples that Jack showed us on Friday. Now, I'm not going to repeat the computation, but another thing we learned from him is that p-derivations do decrease p-adic order in the following sense. You take a p-derivation of some power of p times something else. This is p to the n minus 1 times that something else, mod p to the n. So these were the maps that we were looking for. These are the maps that are going to sort of see what we want for elements in P, for prime integers. And so with this, we can define mixed differential powers. So this is with Alessandro and Jack. So let's say that you hand me a ring that does have a p-derivation. Maybe let me call that p-derivation delta. And give me an ideal where I want to assume that I has p in it. Then the mixed differential powers of this ideal. So I write I n in a little mix. And I should say, feel free to laugh. This is meant to be a pun on the fact that I'm in mixed characteristic, but I'm also going to mix in differential operators and p-derivations. So that's why they're called mixed differential powers. So what are the mixed differential powers? I guess I kind of already said it. I'm going to take my element f. I'm going to apply differential operators of some order. Now there are A linear. So sorry, this is an, I should have said not a ring, but an A algebra. And then I compose with a certain power of the p-derivation that I have. And I want this to be inside the ideal whenever A plus B is at most n minus 1. So here, I'm sort of thinking as my p-derivation as an operator of order 1. And so I'm taking powers of it and thinking of them as differential operators of order A. Sorry, operators, I shouldn't say differential. And so I think of this composition as sort of living in order A plus B. And so the theorem that maybe you're already guessing what it is, but let me write it down. So this is with Alessandro, the Stefani, as are all the new results today. And Jack Jeffries. Maybe I want to keep us looking at it. Okay, so let's say that I take a Z or a DVR. Oh, so sorry. With uniformizer P. And let's say that my ring R is a localization of a finally generated smooth A algebra. And I want to assume that this ring has a p-derivation. Maybe let me call it delta, although delta won't appear in the statement. So for example, take a polynomial ring over an unramified DVR and you're in business. Now take a prime. And I already described what happens to symbolic powers when the prime doesn't intersect A. So we might as well intersect A, right? I want it to contain some prime integer. Sorry. So in the case of Z, the other one, it's that P that we already fixed. And let me also assume, sorry for the long statement, I want to assume that the extension from A mod P to the residue field of R localized at Q is separable. So if you like, this works for every prime if A mod P is perfect. And now the statement that maybe we're already guessing, right? After all this, maybe we're already guessing that the statement is that these mixed differential powers do indeed describe the symbolic powers for all n. So the p-derivations are sort of seeing what happens in the arithmetic direction. And I should say that all these technical assumptions are actually necessary. We have examples showing such things. And I want to sketch this to you. Maybe let me let you stare at the theorem for another second. And essentially the idea of the proof is we prove that these things were cooked up just right to have sort of the minimal properties that you would have to be forced to be the symbolic powers. Okay, so now I want to remember some of those elementary facts I said in the beginning. So here's a sketch, sort of 4 steps. Step 1, show, and you don't need any of these technical assumptions to prove this. You need the Q is a prime containing P. You show that the mixed differential powers contain the powers. And then you show that when Q is a prime containing P, these mixed differential powers are Q primary. So notice in particular that this 1 and 2 imply that these mixed differential powers at least contain the symbolic powers, because the symbolic powers are the smallest Q primary ideals that contain Q to the n. It's one of their basic properties. And so now what you want to do is you want to prove a reverse containment, right? You want to show that the symbolic, that the mixed differential powers now are contained in the symbolic powers. And now here's an elementary fact we all learn in our first commutative algebra course. Containments are local statements. To prove you have a containment of 2 ideals, you just need to prove it after you localize. So sufficient to show after localizing, but you don't have to localize at every prime out there. You just have to localize at the associated primes of this ideal that is presumably bigger, so this symbolic power. But the symbolic power is a Q primary ideal, so its associated primes are just Q. Right? So we essentially just need to prove the situation where you have a maximal ideal. So to complete the story, you prove 2 more things. You prove that taking mixed differential powers is something that commutes with localization. And then you prove that if you have a local ring, then the mixed differential powers are just the powers, which, by the way, are the symbolic powers. Okay. So in a sense, these are sort of the minimal properties an ideal would have to be the n symbolic power of Q. And so this forces the statement to be true. Okay, so one thing that follows from all this that wasn't obvious, and you should have all complained earlier, is that my definition of the mixed differential powers depends on a choice of a p-derivation a priori, as I wrote it. But it turns out it does not, right? Because they're all equal to these symbolic powers. Now, okay, maybe I have 1 minute to make this remark before I move on to part 2. On Friday, Jack told us about this Jacobian criterion in mixed characteristic involving differential operators and p-derivations. So, and he mentioned at the time that you could deduce the case of a hypersurface from this work. So maybe let me make that remark more precise now that we have the actual statement. Let's say, for example, let's say you have now a polynomial ring, you have an F, you have a p-derivation on your polynomial ring, and you have a prime that contains P. So Jack told us about which primes containing P are in the singular locus. So when you localize a Q, this is regular, or I guess maybe let me say not regular. Right? There's a prime in the singular locus. If and only if what? Where if and only if in this quotient, maybe F in the localization lives in the square of the maximal ideal, right? If it's not a linear thing. But upstairs in the original ring R, this means that F is in the second symbolic power. But we just said that the second symbolic power is described by the differential operators of order 1, so d, dx, i's, and now our p-derivation, whether or not this is all in Q. Right? So this is that statement he gave us on Friday. Okay, let me pause for a few seconds just in case there are questions. Okay. So what I want to do in the second half of the talk, which I realize is no longer half time-wise, but anyways, what I want to do now is I want to tell you about a different application of these ideas in a situation where, curiously, I don't know that I have a p-derivation, but somehow I can borrow p-derivations from some other rings to answer a question, again, about symbolic powers. Okay. So the story now begins in the 40s. I guess it all comes back to the 40s today, with the theorem of Chevalley. Chevalley's lemma. What did I do? Oh, wow. Sorry about that. The joys of online talks. Okay, so Chevalley's lemma from 1943. This is the following. Let's say that I have a decreasing family of ideals. So you take a higher n, your ideal is contained in a smaller n, a decreasing family of ideals. And I want to be in a complete local ring. And let's suppose I know that when I intersect all the ideals in my family, that I get 0. So Chevalley's lemma says, well, then there's a rule, a way to assign to each natural number some other natural number, basically so that essentially that there is an element in our family that lives in the nth power of m for every m. So really saying is that the topology determined by this decreasing family of ideals is finer than the ematic topology. And an important special case of course, we're talking about applications of symbolic powers, is when the family we're talking about are the symbolic powers of my ideal I. So flash forward to 2009, and we have a uniform Chevalley lemma by Hunicke, Katz, and Validasti. So 2009. So now let me say again, I have a complete local domain. They proved something more general, but this is what I'm going to need today. Local domain. Then maybe let me put it like this. There exists a constant C such that I symbolic Cn is contained in m to the n for all n. And I want to emphasize that this constant C does not depend on the ideal, independent of I. So they're sort of saying two things. They're saying this function from Chevalley is actually a linear function. And the linear function you put there, the constant, is actually uniform, right? It works for all ideals. So if only we could find explicit instances of this, right? If we could say, for this particular ring, I have this particular seed, this would in particular give us lower bounds for the ematic order of elements in our symbolic power. You remember in the beginning, I said you could find elements in your symbolic power that kind of in the wrong degree, right? We're in the degraded case there, now I'm in the local case. So I want to give bounds for the ematic order of elements in the symbolic power, and this would be one way.
I'm sorry, just a quick question. Maybe I got distracted. Is there any assumption on regularity of R, or any complete local domain is okay?
Yeah.
Okay, thanks.
Yeah. Good question. Fantastic. However, okay, now what happens when you do have an assumption on regularity? Okay, so this is one of those things that I said earlier I was going to remember later. So one of the theorems I called Zariski-Nagata, the one in the local setting, said that I symbolic n was contained in m to the n when r is regular. So it was saying that when r is regular, you can take c equal to 1, right? So what I wish to do is when I'm in a singular setting, I wish to find explicit c's as well. And I can already tell you c equals 1 is not going to work in general, right? So we got to go find, some other c's that work. And so that's what we're going to do with the rest of the time we have. And so I'm shifting a little bit to the graded setting. And let me tell you a situation where we do have bounds for such things. So this is a theorem you'll find in a long survey of symbolic powers. Dow, de Stefani, Hunicke, and Núñez-Betancourt. It's a survey on symbolic powers. It does have several new results, and this is one of them. And so now I have K of fields, and I want to emphasize, I think somebody's going to ask me this soon, it's any field I do not need to assume perfect now, even though it's going to feel like I do when I start talking about the ideas. And I'm going to take a graded algebra. So these FIs are homogeneous. A graded subalgebra of a polynomial ring over K. I'm going to call S. And I don't just want a graded subalgebra. I want a graded direct summand, right? So I want that there's a graded inclusion that splits. And let's say that I now take the homogeneous maximal ideal in R, then for every homogeneous prime, in R, the QDN symbolic powers in Q to the n, where D, this explicit Chevalley constant, is going to be the maximum of the degrees of the FIs. Okay, so very explicit. So the dream, to finish the talk, the dream is to come up with a mixed characteristic version of this. And if I'm going to do that, I better understand first what happens in the field case and what is there that we can and cannot extend. So let me tell you about the key ideas in this proof. So I have my R, including an S. I said it has a graded splitting that I'm going to call little s. So this is a splitting. And we're going to do three things. Maybe first of all, this one's not hard. We're going to show that if we look at the maximal ideal of the polynomial ring upstairs, so I'm going to call it eta, the maximal ideal of the x's, and I take its dnth power and contract to r, that I land inside the nth power, the maximal ideal. And now I'm going to need a lemma by Álvarez-Montaner, Hunicke, and Núñez-Betancourt. That says the following: if you take a differential operator upstairs over the polynomial ring, and you compose your differential operator, I guess I used delta on both. Okay, if I compose my differential operator with a splitting, I do get a differential operator downstairs over the direct summand. And we complete the story by doing the following. You show that when you take the n symbolic power, so for whatever n, I guess in the end, they're going to really use it for d times n. that is always contained in eta to the n contraction with R, right? So then putting this fact together with this fact gives the containment we want. And this is the part I want to tell you a little bit more about. This is the part we want to explore to extend the mixed characteristic. We're going to use this lemma, and we're going to use the fact that upstairs I have a polynomial ring. So the symbolic powers are given by differential powers. Now you should complain and say, wait a minute, you said it was any field, you didn't say perfect. But when you take just a maximal ideal, it is still true that the differential powers are the symbolic powers for maximal ideals, whether or not K is perfect. And the final ideal is the following. So you want to prove a containment, you're going to prove if you take something up here, something not here, it can't be here. And you do the following, okay, F is not in here. So upstairs, it's not in a power of the maximal ideal, so it's not in a differential power of the maximal ideal. So there exists some differential operator of order n-1 that sends F outside of n. But now remember this lemma of Alvarez, Montana, and Hunicki and Espetancourt tell me, aha, compose with the splitting. Sorry, I should keep the same notation. Compose with the splitting. Now you have something that's a differential operator over R. Order n. And now you're going to have something that is not in the maximal ideal downstairs. But of course, the maximal ideal contains the prime we started thinking about to begin with. So we have a differential operator that sends me outside of this prime. So then it's not in its differential power. And I don't know the differential power is a symbolic power anymore, but I don't care because it contains it. That was one of those notes I made at some point that I said I would need. So even though the differential powers no longer characterize the symbolic powers, they contain them in a way that's helpful to still prove things about the symbolic power. So F is not in here, sorry, okay? So if we want to do this in mixed characteristic, it seems clear that, well, let's just replace differential powers with mixed differential powers. Can't we copy the same idea? Well, there is one small problem. There's one thing I don't know the answer to, and I don't think it's known, but if there are any experts in the audience who do know the answer, I would love to talk to you after my talk. So one thing I don't know is if I have a direct summand of a ring that has a p-derivation, I do not know that that forces the smaller ring to also have a p-derivation. And one of the themes we've been hearing about in this program is about direct summands, right? And how direct summands sort of get nice properties. In this case, they're direct summands of polynomial rings. So in fact, on Wednesday, Rankea gave a really nice list of rings that are direct summands over fields. So maybe I'm not going to repeat his list, but let me instead tell you about how we go around this problem of maybe not having a p-derivation, but still solving the problem using p-derivations. So the idea is the following. So let me tell you about the setting. Let's say that you give me a DVR with uniformizer, sorry, this is terrible, uniformizer P, so some prime integer, prime. And let's say that this ring has a p-derivation, oops, with a p-derivation. And let me take now, so now I have a graded subalgebra of a polynomial ring. So the AFIs again are homogeneous. Let me fix a p-derivation over the big ring S. I don't know that I have one on R, but let me assume that at least going mod p, let me assume that I have a direct summand. So there is a splitting, at least mod p. And I do want to point out, this could in principle be a weaker condition than assuming that upstairs I have a direct summand. So Jack Jeffries and Anurag Singh have shown that some classical rings of invariants are not direct summands in mixed characteristic, but they could be in characteristic P. So a priori, this is a weaker assumption. So let's say that I take a prime that contains P. And now I'm going to define, I'm sorry for all the funny powers definitions, but yet a new thing. I don't think we gave this one a name in the paper, but anyway, it's an auxiliary tool that I'm going to use. It's not going to appear in the statement, but I want to tell you what the idea is. So I'm going to ask about the elements. That when I apply differential operators, so let me say, take a differential operator of order A upstairs over the polynomial ring, and then take a power of the p-derivation. So this is all happening, up in S, and then I'm going to apply my splitting, and everything is happening mod p. So this means going mod p, this bar, and I want this to be inside Q, at least after I go mod p. So this looks a little funny, but it's just to give you an idea of what is the technical thing that you need to do, to work. And the point is, one proves that this is going to be a Q primary ideal that contains Q to the n, and so it contains the symbolic power. And then in the end of the day, the theorem we prove, and I see I only have 1 minute, so I'll stop after that. Let me just write down the statement. The theorem is the following. So very, very similar to what we had in over fields. Actually, okay, let me save some time. And I already said that R is a subalgebra vector. It's graded. Let me just write a couple of bits of notation. I want to think about two ideals in R: the idea of the Fs, so the algebra generators, and then the actual homogeneous maximal ideal. And I do want to again take the maximum degree, of all the algebra generators. Okay, so I have two situations now. Primes that contain P and primes that don't. And I actually don't need to assume they're homogeneous. I need to assume that either it's contained in the ideal of the F, in which case I want the actual inclusion to be split. And that's going to tell me that the dn symbolic power is in fact not just in n to the n, but in the nth power of the ideal of the F's. And then when Q is a prime containing P, so now containing the actual homogeneous maximal ideal, I only need to assume that the mod P inclusion splits. And the theorem is now, I guess, what we would expect. And we do have examples showing that these can be sharp, but I see that I'm out of time, so I guess I'll stop there. Thank you.
Thank you very much. Does anybody have questions for Eloísa? Okay, if there are no questions, then let's thank Eloísa again, and I hope to see you all tomorrow. Thank you.